would assume you would have attempted a few problems from the sheet by this time and ready for some discussion at my end. Right, so the sheet titled Journeying Along Differentiability, etc. Journeying along differentiability, etc. So the first problem of the sheet is about a function gx, which is x minus 1 mod ln x. X minus 1 mod ln x. We want to check this function for differentiability at x equal to 1, right? Of course, you can easily see that a revised description of this function would be x minus 1 ln x for x greater than or equal to 1, because when x is greater than or equal to 1, ln x is greater than or equal to 0, right? And is going to be minus of x minus 1 ln x for x less than 1. Yes or no? Because when x is less than 1, ln x is less than 0, mod ln x would be minus ln x. Clear? And therefore, as far as continuity is concerned, limit gx, x tends to 1 from the greater than 1 side. When x tends to 1 from the greater than 1 side, the description of the function is this, right? Which is 0, right? Limit gx, x tends to 1 from the less than 1 side. When x is slightly less than 1, the description of the function is this. Which is also 0. Well, of course, you know, if you have found continuity to be in good stead, then there is need to check for differentiability. However, it would have been good news if the function was discontinuous at x equal to 1, then you won't have to take the pains of checking for differentiability. But now you are entitled, or rather you are obliged to check for differentiability at x equal to 1, right? Because the function has been deemed continuous at x equal to 1. The right hand limit and the left hand limit are equal and both equal to the value of the function at x equal to 1. The value of the function at x equal to 1 is also 0, as you can see, right? Okay. Now, and this, by the way, again, mod ln x is not differentiable at x equal to 1. See, this is the graph of y equal to ln x. This is the graph of y equal to ln x versus x. At x equal to 1, it becomes 0. And if you recall, the graph of y equal to mod ln x is going to be this. I have discussed this thing earlier, right? This would be the graph of y equal to mod ln x. And mod ln x exhibits a sharp corner at x equal to 1 and is not differentiable at x equal to 1, right? So, but x minus 1 is a linear function, a polynomial. This is differentiable everywhere, but this is not differentiable at x equal to 1. However, the product of a differentiable and a non-differentiable function may be differentiable. So we can't draw any conclusion out of this, right? We would actually have to check the function, right? Right hand derivative at x equal to 1, g dashed 1 plus 0 is limit gx minus g1 by x minus 1 as x tends to 1 from the greater than 1 side. What is g1? g1 is 0 anyways, right? So this is like limit gx. When x is slightly greater than 1, this describes gx. So limit x minus 1 ln x by x minus 1 as x tends to 1 from the greater than 1 side, and you can readily see it's going to be ln 1, which is going to be 0. So the right hand derivative at x equal to 1 is 0. Let's check for the left hand derivative at x equal to 1. Clear? Let's check for the left hand derivative at x equal to 1. Right hand derivative is 0. Let's check the left hand derivative at x equal to 1. G dashed 1 minus 0 is going to be limit gx minus g1 by x minus 1 as x tends to 1 from the less than 1 side. G1 is 0. As x is slightly less than 1, the description of gx is this, right? So this is limit minus x minus 1 ln x by x minus 1 as x tends to 1 from the less than 1 side. That's also going to be 0. So the left hand derivative at x equal to 1 is also 0. The function therefore is deemed differentiable at x equal to 1. Both the left hand tangent and the right hand tangent are flushing with each other, in addition to the function being continuous, right? Yes or no? And by the way, sometimes, there could be an issue. You found for a given function, for example, this you must bear in mind. F dash x will give me the slope of the tangent at x, right? You know why that condition for continuity? Say if I had a function like this, this will be the slope of the left hand tangent, and the function is not even defined here. You might erroneously get this as the slope, and these two could be parallel, and you might want to conclude that the function is differentiable at that point, which it is not. So this is an error that occurs sometimes. Therefore, if it was continuous at this point and then this slope became equal to the slope, then this line will become coincident with this line, causing uniqueness of tangency, otherwise not, right? Okay. In fact, at the upper branch where you saw there was a kink, the tangent cannot be even drawn. Tangent cannot be even drawn at that point. There is a function fx which is box x we want to find its left hand derivative at x equal to k, where k is an integer. We want to find the left hand derivative at x equal to k. That means we want to find f dashed k minus 0. Left hand derivative at x equal to k, where k is an integer, box x is the greatest integer function, right? Now f dashed k minus 0 is what? Limit fx minus fk by x minus k as x tends to k from the less than k side. Now fk is 0 because fk means this is an integral multiple of pi. Sign of an integral multiple of pi will always be 0. So fk is 0. This is limit fx. Fx is box x sine pi x by x minus k as x tends to k from the less than k side? Yes or no? Now, when x is in the immediate neighborhood of x equal to k but to the left of k, this is k, this would be k minus 1, and if x is to the immediate left of x equal to k, then box x would be identically k minus 1. Box x would be identically, it will not tend to k minus 1, it will be identically equal to k minus 1. Yes or no? When x tends to k from the less than k side, box x does not tend to k minus 1, it's going to be identically equal to k minus 1. And if box x is identically k minus 1, this will become k minus 1 and k minus 1 will come out. Right? Yes or no? X tends to k from the less than k side. This is what we are reduced to. Yes or no? Now, this would mean, suppose I took x minus k as some h, right? As x tends to k from the less than k side. When x is slightly less than k, h will be less than 0 but tending to 0. H will be tending to 0. H tends to 0 from the less than 0 side. Yes or no? As x tends to k from the less than k side, h will tend to 0 from the less than 0 side, right? This then would reduce to k minus 1 limit sine pi x, x is k plus h by h as h tends to 0 from the less than 0 side. Yes or no? Now this is like k minus 1 limit sine k pi plus kh. What minus? Pi h by as h tends to 0 from the less than 0 side. Yes or no? Now, sine k pi plus theta is going to be what? Now, in this case, this is sine k pi plus theta, where theta is a negative number. See, because h tends to 0 from the less than 0 side, so theta is a negative number. Yes or no? So this actually is of the form k pi minus theta kind of a thing, where theta is positive. Yes or no? Now, there are two possibilities for this. So this pi h is like a minus theta, where theta is positive. Pi h is like a minus theta, where theta is positive. Yes or no? Right? Now, realize that So theta tends to 0 from the greater than 0 side. Theta tends to 0 from the greater than 0 side. As h tends to 0 from the less than 0 side, theta tends to 0 from the greater than. Theta is positive. Theta is positive. Forget that. Look at this first. Two possibilities. K is even, K is odd. Right? When K is even, say for example, sine 2 pi minus theta. Minus sine theta. Sine 4 pi minus theta. Minus sine theta. Yes or no? It will always be a case for the fourth quadrant. When K is even, this will belong to the fourth quadrant, and in the fourth quadrant sign is negative. So when K is an even number, where K is an even number, this then becomes minus sine theta. Right? Now, when K is odd, then say pi minus theta, that will be sine theta. Sine 3 pi minus theta, sine theta, right? So when K is odd, this will be sine theta, yes or no? Clear? And therefore, sine K pi minus theta is going to be minus 1 to power K minus 1 sine theta. Do you realize that? See, when K is even, K minus 1 would be odd and it will become minus sine theta. See, when K is even, K minus 1 will be odd and this will become minus sine theta. That is what you need for K equal to even. When K is odd, it will become plus sine theta, because when K is odd, K minus 1 is even and this will become plus sine theta. Yes or no? Right? So I could have written this as K minus 1 theta is minus pi h, theta is minus pi h. So this is like limit minus 1 to power K minus 1 sine theta. Sine theta means sine minus pi h, sine minus pi h, sine minus pi h. Where h tends to 0 from the less than 0 side. Clear? Yes or no? This minus will come out and will make this minus 1 to power k. I multiply by a pi here and I adjust a pi there. Then I have sine theta by theta, as theta tends to 0, that's going to be 1. So this is K minus 1 minus 1 to power K into pi. Minus 1 to power K. This would become 1 into pi. That's the left hand derivative at x equal to K. Make sense to all of you, right? Actually, I'll tell you, I could have made life a little simpler for you. Let me, I'll just, sorry? Sine minus theta, because pi h is, look, I think I'll simplify matters for you. Let me just say sine k pi plus theta, whether theta is positive or negative, right? Sine k pi plus theta, you'll realize that, you know, it's actually all converging to the same, because the result that I'm going to write will be true whether theta is positive or theta is negative. Sine k pi plus theta, I claim, will always be, whether theta is positive or negative, is going to be minus 1 to power k sine theta. Then theta will bring along its own sign if required here. You don't have to bother. See, when k is even, it will be sine theta. When k is odd, it will be minus sine theta. Yes or no? This is true for all theta, whether theta. So then, why bother about whether theta is positive or negative? Why bother about whether this is positive or negative? Right? It will bring along its own sign. You don't break your heads over the sign at all. Right? Let's make life simple here. So sine k pi plus theta, this could simply have been written as k minus 1 limit minus 1 to power k sine theta. Let sine pi h manage its own sign based on the sign of h. You don't break your heads over it, right? H tends to 0 from the less than 0 side. Clear? Yes or no? And now you multiply and divide by pi into pi. This will be 1. This will be minus 1 to power k. So this then turns out to be k minus 1 minus 1 to power k into pi. That's a left hand limit at x equal to k. Now what about the right hand limit at x equal to k? Everything will remain the same. Sorry? No. This will not change, because whether h tends to 0 from the greater than 0 side or less than 0 side, it will still be this. What will change is this will become, when x is slightly greater than k, box x will be k. That's all. That's the only difference. This will become k if you took the right hand derivative at x equal to k. That box x would be identically k instead of k minus 1. That's the only difference. Yes or no? Right? So is the function differentiable at x equal to k? No, it is not. It is not. This time it's a product of box x, which is not differentiable at x equal to an integer, and sine pi x, which is differentiable everywhere. Right? So this time a product of differentiable and non-differentiable function turns out to be not differentiable. Right? So nothing could be conclusively said about the product of a differentiable and non-differentiable function. You will have to investigate and examine. Got it? Okay. Let's look at the third problem, which is about another kind of formation. Problem 3. Where we have fx given to be x when x is greater than or equal to 0, less than or equal to 1, and is 2 minus x when x is greater than 1, less than or equal to 2. We need to determine the form of a function gx, where gx is f of x, and examine this function for continuity, differentiability, etc. Okay? Now f of x means what? Replacing x by fx wherever it comes. That's f of x. F of x means replacing x by fx wherever it comes. Right? So f of x is equal to fx, where fx lies between 0 and 1. Right? And is going to be 2 minus fx. Where fx is greater than 1, less than or equal to 2. Yes or no? Hey, but this will not do, because we eventually need f of x entirely in terms of x, not fx, right? That's when we'll discover the form of f of x, which could be investigated Is it not? Right? Now, look at, there are two lines of description here. There are two lines of description here. In the first line of description, this fx could either pose to be x or could pose to be 2 minus x. Yes or no? Right? That means, for this, I'll have to look at two further lines of description. One line of description commensurate with fx equal to x. The other line of description commensurate with fx equal to 2 minus x. Right? So this would inflate into two lines of description. Same with this. In this line of description also, fx could either be x or could be 2 minus x. And then therefore, this will also inflate into two further lines of description. So in all, this would really lead to 4 lines of description of f of x. Yes or no? Did you understand this? Fx, look at this, could either be x or 2 minus x. So I'll have to look at one line of description where fx is x and another line of description where fx is 2 minus x. So this would lead to 2 lines of description. Same with this. This will also lead to 2 lines of description. So in all, there will be 4 lines of description of gx. Do you get me right on this? Right? So let's simplify matters by elaborating them. This first line of description, right? So all for gx. Let me take fx as x. Let me choose fx as x. Clear? Now, no matter what I choose as fx, the choice of fx must lie between 0 and 1. So if fx has been chosen as x, then this x must lie between 0 and 1. But the moment you choose fx as x, then this x must also lie between 0 and 1. So it so happens that if fx is chosen as x, then x must lie between 0 and 1. So this condition, along with x greater than or equal to 0, less than or equal to 1, it so happens that they are the same. In the next line, for example, they will not be the same, which you will realize. So the intersection of these two conditions is x greater than or equal to 0, less than or equal to 1. Yes or no? Second possibility. Fx is 2 minus x. Fx is 2 minus x. Right? That's the second possibility for this line of description. Fx is 2 minus x. Now, no matter what you have chosen as fx, fx must lie between 0 and 1. So in this case, 2 minus x must lie between 0 and 1. Right? Hey, but the moment you choose fx as 2 minus x, x must also wriggle between 1 and 2. Yes or no? Right? So x must be greater than 1, less than or equal to 2. Yes. Fx could be x or 2 minus x. Say fx is x. No matter what fx is, fx must lie between 0 and 1. This time fx has been chosen as x. So x must lie between 0 and 1. But if fx is chosen as x, then x must lie between 0 and 1. So both these conditions must be met. Yes or no? Look at the second line of description. It's coincidence that these two are the same. The second line will draw a distinction. Second case, fx is 2 minus x. When fx is 2 minus x, well, 2 minus x must lie between 0 and 1. So 2 minus x lies between 0 and 1. But moment you choose fx as 2 minus x, you must also ensure that x lies between 1 and 2. So x lies between 1 and 2. Both conditions must be met. See, in this case, these are different conditions. It's a matter of chance because of the nature of the expressions that both these conditions are the same. In this case, the distinction has been clearly drawn. Is that all right? Okay. So this line completely taken care of. Let's move to this line. Again in this line, fx could be x or fx could be 2 minus x, right? Say fx is x. Say fx is x. No matter what your fx is, that fx must lie between 1 and 2. So x must lie between 1 and 2 this time. fx is x, so this will be 2 minus x. 2 minus x, fx is x, so this will be 2 minus x. And 2 minus x must be greater than 1, less than or equal to 2. I'm so sorry. Fx is x. X must lie between 1 and 2. Right? I repeat. This line of description, I have chosen fx as x. Right? So, if fx is chosen as x, x must lie between 1 and 2. Hare Baba, listen to me properly, yaar. Please listen to me. Just this condition. Fx has been chosen as x. So fx, which is x, must lie between 1 and 2, which is this condition. Along with, the moment you choose fx as x, x must lie between 0 and 1. Yes or no? Right? The fourth line. This fx could be 2 minus x. So this will become 2 minus x. Now, the moment you choose fx as 2 minus x, then 2 minus x must lie between 1 and 2. Along with, the moment your choice of fx is 2 minus x, x must also lie between 1 and 2. Right? Yes or no? Does it sound good? Right? These are 4 lines of description. Let's simplify these lines of description further. Right? Gx, which is f of x, is x. This intersection, this would be x greater than or equal to 0, less than or equal to 1. Right? The second line of description, 2 minus x, 2 minus x. When this is 2 minus x, look at these conditions. 2 minus x greater than or equal to 0, less than or equal to 1 would boil down to what? 2 minus x less than or equal to 1 greater than or equal to 0 would boil down to x greater than or equal to 1 less than or equal to 2. Yes or no? So this condition would boil down to x greater than or equal to 1 less than or equal to 2, and this is x greater than 1 less than or equal to 2. If you look at the intersection of these two, what would it be? X greater than 1 less than or equal to 2. This will be x greater than 1 less than or equal to 2. That will be the common region to these. Did you understand from 2 minus x less than or equal to 1 greater? You didn't understand this? Okay, Sparsh. Look at this side of the inequality. Bring x on this side and 1 on this side. You get x greater than or equal to 1, isn't it? This side of the inequality. Now look at this side of the inequality. You get x, bring x on this side, leave 2 on this side, less than or equal to 2. This is what you get. Yes or no? Right? And this along with this condition must hold good. X must be greater than 1 less than or equal to 2. If I look at the intersection of these two, what will I get? X greater than 1 less than or equal to 2. So the second line is x greater than 1 less than or equal to 2. Yes or no? Now let me look at the third line of description. So can I just remove the clutter from here? The first 2 lines can I remove and examine the third and the fourth? Okay. Look at this third line of description. That's 2 minus x. X greater than 1, less than or equal to 2. And x greater than or equal to 0, less than or equal to 1. What's the common region to this? Is there any common region? So what is this? Null set. This is a null set. So this is junk. This line of description can be disregarded. There is no such line of description, that means. And I'm expecting this. Why? Because see, I already have a full description from 0 to 2. And I'm expecting now the other two lines to be dumb lines. Right? So now look at this line, which is x. And look at these two descriptions. This description is like x greater than or equal to 0, less than 1. See, if I transpose x on this side, I get x greater than or equal to 0. If I transpose x on this side, x less than 1. X greater than or equal to 0, less than 1, intersection x greater than 1, less than or equal to 2. What common region do I have for this? Expected this, right? No common region between these two ranges of x, right? So this is also junk. Yes or no? So these two lines can be ignored. We have f of x described completely in the first two lines for x lying between 0 and 2. Clear? Yes, it's the same as fx. It's the same as fx. See, if I have to draw the graph of gx, that is f of x, then in the interval 0 to 1, it goes as a straight line y equal to x. When x lies between 0 and 1, it goes as y equal to x. At x equal to 1, it assumes a value 1. At x equal to, and then from 1 onwards, 2 minus x, a decreasing slope, right? A decreasing line. So then, and again, the right hand limit at x equal to 1 is also 1. See, the right hand limit at x equal to 1 is 1. The left hand limit at x equal to 1 is 1. The function is continuous at x equal to 1, but it now goes as y equal to x minus 2 in the interval 1 to 2. It is not differentiable at x equal to 1, even though it's continuous at x equal to 1. The left hand derivative is the slope of this line, 1. The right hand derivative is the slope of this line, which is 1. 2 minus x, sorry, this is 2 minus x, y equal to 2 minus x. The right hand derivative is minus 1. The function is not differentiable at x equal to 1. The function is not differentiable at x equal to 1. Yes or no? Got me? Left hand derivative you can obtain by differentiating this with respect to x, dy dx, which is plus 1 at x equal to 1. Differentiate this with respect to x and plug in x equal to 1, minus 1. You get the right hand derivative. Right? So the function is not differentiable at x equal to 1. One thing which I want to mention. If say this is y equal to fx, some graph y equal to fx versus x. This is a given x and this is fx. Geometrically, I want to find f of x. Geometrically, I want to find f of x. Right? Yes or no? What I do is, in order to geometrically find f of x, take this line y equal to x. This is a line y equal to x. This is a line y equal to x. Alright. This is the point P. Draw a line parallel to the x-axis to intersect y equal to x at P prime. Right? Now, do you realize that if this is fx, this length is fx, this length will also be fx? Yes or no? This length will then be fx. Say MP prime will also be fx? Yes or no? Right? Now, if MP prime is fx, this angle is 45 degrees. So then, can I say OM will also be fx in length? OM will, because this is fx, OM will also be fx in length, right? So OM will also be fx in length, right? Now if OM is fx in length, that means the x coordinate of M is fx, x coordinate of M is fx, yes or no? So just draw it on a separate plane, just for the sake of neatness. This was the curve given, and I've been able to locate a point M. I've been able to locate a point M whose x coordinate is fx. Yes or no? Whose x coordinate is fx, right? And from M, I draw this vertical line and get this point MQ. This will be the point Q on the graph of the function. This will be the point Q on the graph of the function. Yes or no? And this is the graph of the function y equal to fx, right? This length would be f of x naught. This length therefore would be f of x naught, yes or no? For a given x, this will be f of x, right? So if this is x naught, this will be f of x naught. F of x naught. But x naught is fx, so this is going to be f of x. That's how you can geometrically locate f of x. Drawing a line y equal to x. This is fx for a given x. Draw a line parallel to the x-axis, intersecting the line y equal to x at P prime. The projection of P prime would be M, whose x coordinate will be fx, and therefore this length would be f of x. Using this time, the previous problem that I did, right? The previous problem that I did, fx equal to x for x lying between 0 and 1, and is 2 minus x for x lying between 1 and 2. If you draw f of x in a manner that I have suggested, you will find the same graph of f of x. And then all those 4 lines of description, those would have been considered unnecessary, right? We could have geometrically obtained f of x using this algorithm. All right, work on it independently, but you've understood both the things, right? How on a given graph of a function y equal to fx, you could locate f of x. Given fx, how do you locate f of x geometrically? Clear? Okay. We have a function fx defined as x squared mod cos pi by 2x when x is not 0 and is equal to 0 when x is 0. We want to find f dash 0. Hey, one thing. The function must be continuous at x equal to 0. Just perform a quick check on it, right? A quick check on continuity at x equal to 0. Limit fx, x tends to 0. Because just in case this does not exist, we'll be saved of the trouble of checking for differentiability, right? As x tends to 0, now when x tends to 0, x is not 0. That means x lies in the neighborhood of x equal to 0. Now if x lies in the neighborhood of x equal to 0, this is the description. This is not the description. Right? This is the description for the neighborhood of x equal to 0. So this then is limit x squared mod cos pi by 2x, x tends to 0. Now, as x tends to 0, realize that this will be bounded. Cos of this will lie between -1 and +1, so mod will lie between 0 and 1. Yes or no? So this is bounded. No matter what pi by 2x is, this will be bounded and finite. Right? This will tend to 0 into a finite number, that's going to be 0. Right? Very good. So limit fx x tends to 0 is 0 and is equal to the value of the function at x equal to 0. The function therefore is deemed continuous at x equal to 0. Therefore, we have the green signal to go ahead and check for differentiability at x equal to 0. Okay. F dashed 0 is limit fx minus f0 by x minus 0 as x tends to 0. Yes or no? But f0 is 0. So this is like limit fx, which is this. Right? That's f dash 0. Realize that this will be bounded and finite into 0 will give me 0. Right? So the derivative of the function at x equal to 0 is 0. Yes or no? Right? Now the next part of the problem, we'll have to figure out whether f dash to 1/3 exists or not. Right? F dashed 1/3 is going to be fx limit fx minus f 1/3 divided by x minus 1/3 as x tends to 1/3. Yes or no? Now what is f 1/3? Would have to be obtained from this. That's going to be 1 by 9 mod cos 3 pi by 2, which is 0. Right? Okay. This then is limit fx, which is this, yes or no? Right? This will be f dashed 1/3 if at all. Right? What I do is, let me take x equal to 1/3 plus h. So as x tends to 1/3, h tends to 0. Yes or no? As x tends to 1/3, h tends to 0. This then would reduce to as h tends to 0? Yes or no? Divided by h. Divided by h. Clear? This I can further write as limit h tends to 0. Now this would be 1 by 9 plus 2h by 3 plus h squared. When I divide by h, I get 1 by 9h plus 2 by 3 plus h, right? Mod cos 3 pi by 2 into 1 plus 3h. Yes or no? I hope you realize what I've done here. I've expanded this and divided by h. Then this is what happens. So far so good. Now, can I remove all of this? See, I took x equal to 1/3 plus h, right? If x tends to 1/3 from the greater than 1/3 side, then h will tend to 0 from the greater than 0 side, right? As x tends to 1/3 from the less than 1/3 side, h will tend to 0 from the less than 0 side. Yes or no? Right? So h tending to 0 from the greater than 0 side would give me the right hand derivative at 1/3. This will give me the right hand derivative at 1/3. Where h tends to 0 from the less than 0 side will give me the left hand derivative at 1/3. Yes or no? Right? Let me find, let's say, the right hand derivative at 1/3. Where as x tends to 1/3 from the greater than 1/3 side, h tends to 0 from the greater than 0 side. Yes or no? Right? Okay. So f dashed 1/3 plus 0, which is the right hand derivative at x equal to 1/3. This would be obtained by h tending to 0 from the greater than 0 side, right? This will be the right hand derivative at 1/3. The left hand derivative would be h tending to 0 from the less than 0 side, right? Now realize this. When h is slightly greater than 0, when h is slightly greater than 0, okay, then 3 pi by 2 into 1 plus 3h. Refer to this angle. This is cos theta. This is, if h is greater than 0, this will be less than 3 pi by 2. Yes or no? This will be less than 3 pi by 2. That means this angle will be in the third quadrant. In the third quadrant, cos theta is negative. So mod cos theta would be minus cos theta. Yes or no? Right? So when h tends to 0 from the greater than 0 side, this mod cos theta would be minus cos theta. Do you all understand this? Right? Minus so far so good. Mod cos theta would be minus cos theta. If h tends to 0 from the less than 0 side, see, if h were to be tending to 0 from the less than 0 side, that will be the left hand derivative at 1/3. Then 3 pi by 2 into 1 plus 3h. This would be less than 1 and this will be greater than 3 pi by 2, which is fourth quadrant, in which cos would have been positive. Mod cos theta then would have been plus cos theta, right? Mod cos theta would have been plus cos theta, right? So the only difference between h tending to 0 from the greater than 0 side and h tending to 0 from the less than 0 side is in the greater than 0 side you have a minus sign, in the less than 0 side you don't have a minus sign, right? That's the only difference, algebraically speaking. Clear? Now notice, as h tends to 0, this into this will tend to 0, because, right? 2/3 into this will tend to cos 3 pi by 2, which is 0. So the only term to deal with is 1 by 9h into this, because the other two terms will go into oblivion as h tends to 0, right, Prince? Right? Let me take the minus out. H tends to 0. What do you say to this? So far so good. I hope you realize that the other two terms vanished as h tends to 0. Right? Now, look, it would have been so much better if there was a sign here, because then we would have like a sign by sign as something tends to 0. Sign something by something as something tends to 0 would have reduced to a standard limit. Yes or no? Right? Presence of cosine is an issue here. Now, yes, realize that sine, and I want to do it in terms of 3 pi by 2. Do you realize that sine 3 pi by 2 minus theta is minus cos theta? Is minus cos theta? Yes or no? So this minus cos theta that you see here could have been written as sine 3 pi by 2 minus theta. See, if there was a pi by 2, I would have written sine 90 minus theta as cos theta and used that. But since there is a 3 pi by 2, then in terms of 3 pi by 2, I do this manipulation. I hope all of you understand this. Right? So then, minus cos theta I write as sine 3 pi by 2 minus 3 pi by 2 into 1 plus 3h by 9h as h tends to 0 from the greater than 0 side, right? Which is to say, this is limit h tends to 0 from the greater than 0 side, sine 3 pi by 2, 1 plus 3h minus 1, so 3h by 1 plus 3h by 9h. Yes or no? As h tends to 0? I hope you I took 3 pi by 2 common, so 1 plus 3h minus 1 is 3h by 1 plus 3h. Yes or no? Which then is limit h tends to 0 from the greater than 0 side, sine 9 pi h divided by 2 into 1 plus 3h divided by this 9h I write as 9 pi h by this, so that I have a sine theta by theta kind of a format. So I write this 9h as 9 pi h divided by 2 into 1 plus 3h, and then I do a balancing act here. This pi divided by 2 into 1 plus 3h as h tends to 0 from the greater than 0 side. Yes or no? Yes, so now this reduces to sine theta by theta as theta tends to 0. That's 1. And this will become pi by 2 as h tends to 0. Yes or no? Yes, right. So this is, thank you, sir, pi by 2. Right? Right? So the right hand derivative at 1/3 is pi by 2, and if you took h tends to 0 from the less than 0 side, this minus would be missing and you would get minus pi by 2, right? So f dashed 1/3 plus 0 is plus minus is pi by 2 as you get, and f dashed 1/3 minus 0 will be minus pi by 2. So is the function differentiable at x equal to 1/3? No. In fact, check this out for yourself. Can I wipe this off? Have you registered these ideas? Right? In fact, you might want to check the truth of this statement. The given function would not be differentiable every time x equal to 1 by an odd number. That means x equal to 1 by 2r plus 1, it will not be differentiable. You can check that out. X equal to 1 by an odd number, it will not be differentiable. This is 1 by 3, 1 by 5, 1 by 7. At all these points, this given function will be not differentiable. You can actually perform a check. Same way. See, instead of 3 pi by 2, you will get 2r plus 1 pi by 2, 1 plus, etc. And the same manipulation, right? And then express in terms of sign. Yes or no? No. See, in this case, there are, let me tell you, very two distinct regimes. When the algebra is complicated and the graph is simple, we go for the graph. When the graph is complicated and the algebra is simple, we go with the algebra. In fact, for drawing the graph of this, we'll have to do the algebra. Then why draw the graph first, right? All's good? Okay, here we have this function fx. A to power, hello, 2 times box x plus fractional part of x minus 1 divided by 2 times box x plus fractional part of x. This when x is not 0 and is ln a when x is 0. Clear? Hey, one thing. Box x is x minus fractional part of x, right? So box x plus fractional part of x is x. Box x plus fractional part of x is x. Add box x to both sides. So x plus, or rather 2 times box x plus fractional part of x is x plus box x. Yes or no? Yes or no? So we write this whole thing as x plus box x right here. Now, at x equal to 0, let's figure out the continuity requirements, right? Limit fx, x tends to 0 from the greater than 0 side. Now when x is slightly greater than 0, box x is identically 0, right? Box x is identically 0. It's not tending to 0, I repeat, it's only identically 0. So a power x minus 1 by x as x tends to 0 from the greater than 0 side. And what is this supposed to be? ln a, right? So the left hand limit at x equal to 0 is ln a, right? Right hand limit at x equal to 0, beg your pardon. Left hand limit at x equal to 0, limit fx Now, when x is slightly less than 0, what is box x? Minus 1, right? So, a power x minus 1 divided by x minus 1 as x tends to 0 from the less than 0 side. Now, in this case, this is trivial because both numerator and denominator are defined. I mean, this function is defined at x equal to 0. Therefore, it's simply going to be the value of this function at x equal to 0, which is like minus of a power minus 1 minus 1. Function is not continuous at x equal to 0. And therefore, good for us, good riddance to differentiability for this case, right? We don't have to check for differentiability. Let's look at the next one. F2 minus 1 F2 minus 2 plus 1 minus 1, right? Now in all these cases, look, the next problem is a simpler version of what we refer to as functional equations. Okay, now these functional equations are extremely important in terms of how to deal with them. There are many ways we could deal with functional equations, but a couple of things I'll deliver with the aid of this example, right? But then there are many more ways of dealing with functional equations. The two most important I'm going to deliver using this as my mouthpiece. Okay, the functional equation, like you can see here, is f of x plus y by 2 by 2 for all x, y belonging to the set of real numbers. It's given that derivative at x equal to 0 is minus 1 and the value of the function at x equal to 0 is plus 1. We want to be able to find f2. Right? Hey, almost indiscriminately, almost, save some of those very rare cases, but almost indiscriminately, the thing that you need to do with these situations is, these functional identities, is step 1, close your eyes. Step 2, open them. And then write f dash x, the expression for f dash x. You can skip step 1 and step 2 if you like. Yeah. Okay. Step 1 was close your eyes, step 2 open. You can skip these 2 steps if your eyes were already open. Alright, f dash x. First principles, f dash x is going to be limit f of x plus h minus f of x by h. Right? As h tends to 0? Yes or no? Now, the next step would be deployment of this identity somewhere here. Because, you know, this character has to be drawn into this by some means. Right? What is this? This is f of London plus Patna by 2 is f of London plus f of Patna divided by 2. Yes or no? Now this f of x plus y, if I have to deploy this character, this could be written as f of 2x plus, or rather f of x plus h. 2x plus 2h by 2, yes or no? Right? F of London plus Patna by 2, That's going to be f of London plus f of Patna divided by 2, right? This is going to be f of 2x plus f of 2h by 2 using this condition. F of London plus Patna by 2 is f of London plus f of Patna divided by 2. Yes or no? So this f of x plus h I write as limit f of 2x plus f of 2h by 2. What do you say? Same with fx. I'm going to give fx the same treatment. Can I wipe this off? Fx I can write as f of 2x plus 0 by 2. Can I do this? Yes or no? So f of London plus Patna by 2, which is going to be f of London plus f of Patna divided by 2. Yes or no? Right? How about it? Now this f2x will get cancelled. This is limit f of 2h minus f of 0 divided by 2h, as 2h tends to 0. Yes or no? Hey, f of limit f of something minus f of 0 by something minus 0, as that something tends to 0 is going to be what? F dashed 0. It's going to be f dashed 0. So this is f of something minus f of 0 by something, as something tends to 0. This is going to be f dashed 0. But f dash 0 is minus 1. F dash 0 is minus 1. Hey, it means what? F dash x is minus 1. That means at any point the slope is minus 1. Therefore, fx must be a straight line, so that its slope at any point is minus 1, right? Y equal to fx must be a straight line. It's only a straight line where the slope is the same at every point. Clear? Right? Forget it. I'll just do it on the board for you. Okay? Look at this. F dash x is minus 1. Alright. ddx of fx is minus 1. Right? Kushal. D of fx is minus dx. Yes or no? Integrate both sides. So you get fx equal to minus x plus a constant of integration. But it's given that f0 is 1. At x equal to 0, the value of the function is 1. So since f0 is 1, that means 1 equal to minus 0 plus c. c is 1. Right? So fx then turns out to be minus x plus c. Minus x plus 1. No? Lost? See again, what I was saying earlier, Kushal. F dash x is minus 1. It can happen only for a straight line. Slope of the tangent at any point is minus 1. F dash x means slope of the tangent at any x is minus 1. That can happen only for a straight line. So fx versus x must be a straight line. So fx must be of the form ax plus b, where a must be minus 1 because the slope is minus 1. Y equal to mx plus c. A is minus 1, c you can obtain. That was my earlier remark, which could be also represented this way. Got me? So one thing, modus operandi, starting with an f dash x, taking it to the next step where the functional identity is deployed in expression of f dash x. Having found f dash x from whatever is given, recover fx by integrating. Recover fx by integrating. And there you go. Now, yeah, I'm coming to that. A graph. Let me do it graphically also for you. Okay. Let me also do it graphically for you. But how do you know fx versus x is a linear expression? How do you know that? No, 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 no. It could be a logarithmic function. F of x plus f of y is f of xy. What do you do there? Right? No, you cannot. You cannot. You should not, until and unless you have rock solid proof that it's going to be a linear expression. A geometric way I will suggest now, which will work as good for situations of this kind. Okay. So the next one which will come in handy is the following. Okay. Let's say this is the graph of the function. At x equal to a, its value is f of a. At x equal to b, its value is f of b. This point has coordinates a comma fa, whereas this point has coordinates b comma fb. Right? Look at this second AB. Look at a point C with x coordinate a plus b by 2. Right? Let me call it D, let me call it E. Do you realize that CE then, if this is x, this would be fx, C therefore would be f of a plus b by 2? Right? Now, a plus b by 2 is halfway between these two, right? This is to this is 1 is to 1, isn't it? This is to this is 1 is to 1. So AD on the second, AD is to DB will also be 1 is to 1. Right? So the y coordinate of D would be y of A plus y of B by 2. Section formula, yaar. Zombie didn't catch enough sleep at night. What were you doing? We'll discuss that later. Y of D is y of A plus y of B by 2, right? Y of D means what? CD. Y of D is CD, which is going to be from section formula YA plus YB by 2, right? So that's going to be f of A plus f of B by 2. Yes or no? So geometrically we have been able to locate this as f of A plus B by 2 and this is FA plus FB by 2, right? But what's given in the problem is f of A plus B by 2 equals f of A plus f of B by 2. That's given in the problem. That means what's given is CD equal to DE. If CD is DE, that can happen only if A D coincides with E. That can happen only if D and E coincide. If D and E coincide, that means this graph must be a straight line. Y equal to fx must be a straight line. You will have to hammer E down. So that E coincides with D, and then the graph of y equal to fx will be a straight line. Turns out to be a straight line with A, D and E coincident and B like this. Fx therefore will be a linear function of x. Fx therefore will be a linear function of x, because fx versus x is a straight line, right? So fx then must be of the form Lx plus n. L is the slope. The slope at 0 is -1. Slope at any point will be -1. So L is -1 for this. And m, using the fact that f0 is some value, m can be found. Right? That's a geometrical way of looking at it. The geometrical way may not always work. F dash x will always work. There are some variants around this f dash x which we will learn as we chug along, but to begin with, this is a good starting point. Right? All's good? Let's look at the next one. No, if this type, yeah. Yes, I agree with you. Fx is given such that limit as x tends to 0, fx minus fkx by x is alpha. And we want to check on f dashed 0. Given this, we want to check on f dashed 0 in terms of alpha and k. In terms of alpha and k, I want to find f dashed 0, right? This is given and I want to find f dash 0 in terms of k and alpha. Clear? F dashed 0 is going to be limit fx minus f0 by x minus 0 as x tends to 0. That's f dash 0. I want to deploy this fkx somewhere. So then a very ordinary manipulation that would occur to us is this. I do a fx minus fkx by x plus fkx minus f0 by x as x tends to 0. Right? This will be limit of this plus limit of this. Now, this first one is alpha, that's given. And all of this is f dash 0. That's alpha. This will be alpha plus this would be limit fkx minus f0 by kx. And I balance it here as x tends to 0. X tends to 0 means kx also tends to 0. So this is f something minus f0 by something as something tends to 0. That's going to be f dash 0, right? So this is going to be alpha plus k times f dash 0. This is all f dash 0. Now solve for f dash 0 by transposing f dash 0. Then turns out to be alpha by 1 minus k. Have you attempted problems beyond this? Hmm? I want you to think why k lies between 0 and 1. Please think about it. Given minus a to plus a, why would it be advisable to have k lying between 0 and 1? Please think based on the domain of this function. Think based on the domain of this function, you'll realize why k has to lie between 0 and 1. I mean, that will ensure all the time that kx is in the neighborhood of x equal to 0. If k was a very large number, kx could go way beyond, right? Even when x is small, kx could be very large and may not really be in the neighborhood of x equal to 0. Okay, let's look at the next one. F is a real valued function. F0 is 0. And we want to find F1. We want to find F1. See, put y equal to a, say. Y equal to a. So we have mod of fx minus fa less than or equal to x minus a whole square. Right? Divide by x minus a. Mod of right? Take limit as x tends to a of both sides. And this is any real a. This is for any real a, this condition, right? What is this? Mod f dash a less than or equal to 0. But modulus can never be negative. So the only possibility is modulus must be 0. So the only possibility is f dash a equal to 0. And this is true for any a. This is true for any a. So can I say this would mean that f dash x in general is 0? When would f dash x be 0? When fx is constant. Constant. That means if fx is a constant function and if f0 is 0, f1 we have to find, right? So f1 must also be 0. This one? After this? How divided by x minus a? Right? Got it? Spush. Fx is constant, f0 is 0, so f1 will be 0, f root 2 will be 0, etc. Yes, 9 part 1, we want to be able to discuss y equal to fx equal to mod of mod x minus 1 for all x belonging to the set of real numbers. Right? Let's draw the graph of this. Let me first draw the graph of y equal to mod of x minus 1. This is the graph of y equal to mod of x minus a in general. Yes or no? No? Have I discussed this in the past? Right? Mod of x minus a would have a transition at x equal to a. Mod of x minus 1 has a transition at x equal to 1. Right? From fx to f mod x, this is the graph of y equal to fx. I want to draw f mod x. That means replacing x by mod x here. What would you do? Retain the portion to the right of the y-axis and reflect this portion about the y-axis. Yes or no? So then very clearly continuous everywhere, but not differentiable at minus 1, not differentiable at 0, not differentiable at 1. It's continuous everywhere, but not differentiable at x equal to plus minus 1 and at x equal to 0. The left hand derivative here is minus 1, right hand derivative is plus 1. Left hand derivative is minus 1 plus 1, right hand derivative is minus 1 plus 1. Yes or no? So not differentiable at x equal to 0 plus minus 1 and continuous everywhere. Minimum of x and x squared. This again is a very commonly occurring format. And have I told you how to draw the graph of this? It's kind of a situation now. What you do is, in order that you can draw the graph of this, these are two functions, x and x squared, right? For any given x, one of them will be larger, the other one will be smaller. For any given x, select the one which is smaller. If it was max, then select the one which is larger. That will give me fx. You can choose any real number x, find the value of x, find the value of x squared. Then the smaller of the two will give me min. If it was max, then I would have to select the larger of the two, x and x squared, right? These problems are handled graphically. Draw the graph of y equal to x and the graph of y equal to x squared. Okay. In the same plane, y equal to x is the straight line. This is the line y equal to x, right? Right? Y equal to x squared is a parabola, right? X and x squared become equal at x equal to 1. In the interval 0 to 1, x square will be smaller than x, very clearly. In the interval 0 to 1, x square will be smaller than x, right? That's why the parabola is below y equal to x. Now, look at, so in minus infinity to 0, which is bigger? X square is bigger or x is bigger? X squared, because this is positive. At any given x, this is y equal to x. X is negative. So x square is bigger. So retain the one which is smaller, minimum. Remove this. Okay. In the interval 0 to 1, which is smaller? X square or x? X square is smaller. So remove x. And then again for x greater than 1, x is smaller, x square is larger. Right? So retain x. This is the graph of y equal to minimum of x and x squared. See, minus infinity to 0. For any given x, this is x squared and This is x. Which is smaller, x squared or x? X is smaller because x is negative here. So from minus infinity to 0, y equal to x is smaller than y equal to x squared. So retain the one which is smaller, right? In the interval, refer to the original figure, x square was smaller, the parabola was below y equal to x, so retain x squared. 1 onwards, x square overtakes y equal to x, so retain y equal to x for that interval. Very clearly, it's not differentiable at x equal to 0, at x equal to 1, it's not differentiable but continuous everywhere. Part 1. Fx is a continuous function in the interval 1 to 3. And Fx assumes only rational values. It's also given that F2 is 10. We want to be able to find F3. We also want to be able to find F dashed 1.5. Right? Now, Fx is continuous in the interval 1 to 3. Right? In the interval 1 to 3, Fx is continuous. And it assumes only rational values. Look at 2 points in the interval 1 to 3. Say x equal to a and x equal to b. Fa is a rational number R1. This is Fa, which is a rational number R1. Fb is a rational number R2. F of A is a rational number R1 and f of B is a rational number R2. Because it assumes only rational values. Now, if it is continuous in the interval 1 to 3, it must be continuous over any subinterval a to b, right? Now, realize that if this is rational and this is rational, it will assume all possible values between R1 and R2. Yes or no? Intermediate value property. The function will assume all values between R1 and R2 in the interval a to b. Can I say that? Right? All real values between R1 and R2. That's intermediate value property. In the interval a to b, the function will assume all possible values between fa and fb. If it's continuous, right? Hey, but between two rational numbers, you can always find an irrational whole. Yes or no? Right? So, there would be a value of x, call it c, in the interval a to b, for which the function would be irrational. Irrational? IR. That means there is a contradiction. If the function assumes different values at different points, then the function will assume rational as well as irrational values. If there is a continuous function and it assumes distinct values, it assumes different values at different points, then it is not possible that it assumes only rational values or it assumes only irrational values. That's not possible. Yes or no? However, if I have a continuous function of the kind y equal to fx, which is a constant function in the interval 1 to 3, and say at x equal to 2, it is 10, then at all x it will be 10, and it will assume only rational values. That means this function has to be a constant function. If it was a non-constant function, if fx was a non-constant function and maintained continuity in the interval 1 to 3, then it cannot assume only rational or only irrational values. A continuous function can assume only rational or only irrational values in an interval, provided it's a constant function. So fx must be constant. Fx must be equal to 10 for all x. So f3 will be 10. For derivative at any point will be 0. Right? Yes or no? Clear? Right? Shall we proceed? We want to be able to find limit sine box of cos x one plus box cos x tends to 0. Now in the neighborhood of x equal to 0, realize that when x is slightly greater than 0 or less than 0, cos x will lie between 0 and 1. Because even when x is slightly negative, fourth quadrant case, it will be positive. So in the neighborhood of x equal to 0, on either side of x equal to 0, cos x will be less than 1 and greater than 0. Right? So box of cos x in the neighborhood of 0 will be identically 0, will not tend to 0, will be identically 0. So the numerator would be identically 0, the denominator would be identically 1, so this limit would be 0. Right?